Good morning, good afternoon, good evening, everyone. Welcome to Eliis Technical Forum. We are delighted to have you on board today. I'm Emmanuel Bodia, I'm Product Marketing Manager, and I will be your host for today. So we have set up a very interesting and exciting program for you today, and I hope you will enjoy it as much as we do. Before diving into the presentations, I'd like to say a few words about the Livestone platform. That's the platform we are using today for this event. The session will be recorded, so you can ask for the link to the recording after the event, and we will share it with you. We won't be able to share all the presentations, but we will share Eli's presentations at least. First of all, if you look at your right-hand side, you see that you have the chat box here where you can put any comments, say hello, or any issues, and then we can help you dealing with the issue. If you look at the bottom part of it, you can see that you have a tab questions, and I encourage you to ask your question through this tab questions during the presentation, as we will have 5 minutes Q&A session after each presentations. You'll also see that on the left-hand side of the question, you have the choice to vote for the question. So I also encourage you to vote for the question, as we will prioritize the questions with the number of votes. Okay, so now let's have a look at the agenda for today. So the session will be split into two parts. The first part will be dedicated to Eliis and partners presentations, and then we'll have a 5-minute break. And after that, we have two case studies from our PaleoScan users. So in the first part, we'll have a 10 minutes introduction from Marion Barret, our product manager, and she will share with you what happened for Eliis in 2022 and also the main highlights of PaleoScan 2022. After that, we'll have a presentation from with Aurélien van Velden from Bluware and Jean-Philippe Adam from Eliis, presenting the Bluware FAST technology embedded into PaleoScan. And then the last presentation of the first part will be dedicated to the new structural framework workflow, combining both Petrel and PaleoScan technologies. And that will be given by Benjamin Duro from Eliis and Matthew Elwood from Schlumberger. After the break, we'll reconvene and we have two very interesting presentations. The first one by Adila Mansour from the University of Malaya, and she will present tidal influence fluvial channel system in the Malay Basin. And then after this presentation, we'll have Siti Sarah from DGEG presenting characterization of karst in Luconia province. So very interesting presentations. So that's it for my part. So I wish you a very good event and enjoy.
Welcome, everyone. So I'm pleased to welcome you to this 2022 Technical Forum. So to start, I want to share with you just a few words about this year because it has been really intense and very rich for Eliis. So let me share. Yeah, perfect. So first of all, the Eliis team is getting bigger and bigger. So we have a new office in Middle East in Dubai. You can see that each subsidiary has grown a lot this year. And we have now new retailers around the world. And this is really fundamental because it enables us to build a closer relationship with our customers and so, with you. 2022 is also a year during which we have done a lot of exciting collaborations. And this is mainly because at Eliis, we believe that to tackle the huge energy challenges we are facing, the best-in-class applications need to be combined to enable transformational workflows. This is why we are working closely with other software vendors to facilitate the interaction in between our cutting-edge technologies. So you can see Ion Logics, Petrel or FAST from Bluware. And we will present you in the first part of this technical forum, the structural framework workflow built with Petrel, and as well as the integration of a Blueware technology named FAST into our application. We have also done some, we have also studied inspiring collaboration with 45.8, but also strengthen the one we have with ExploCrowd. And this is because we want to push forward our technology PaleoScan to contribute and accelerate the helium and natural hydrogen exploration, but also virgin reservoirs identification for CO2 storage. Our ambition is to be the reference in seismic interpretation, and to achieve this goal, we are driven by key strategical themes, and I'm going to present you the three main ones our development team is working on. So the first one is related to the fact that the energy industry's success depends on its ability to unlock the enormous digital opportunity offered by the data. And the OSU Data Platform initiative is a great example of how collectively an open source standard-based data platform can be built, and an application such as PaleoScan needs to adapt to that new data-centric era to fulfill these standardization and cloud requirements. So Jean-Philippe and Aurélien from Bluware will present you in a minute our first step, the first step of PaleoScan VDS OSU journey. We are also working on how to integrate 1D, 2D, 3D data in order to enable, to build comprehensive and detailed geological interpretation. And this trigger work on our 2D workflow, on the well data, and also on the functionalities that allow you to do some fine-scale reservoir interpretation. And addressing this challenge, in particular the 2D, is a key, in particular because we want to be much more involved in CCS projects. Finally, we continue our efforts on the user experience and how to bring the guidance closer from our customers. We want to share with you all the experience we have gathered internally, all our tips and tricks to make sure you can become tomorrow experts. On top of this, we also have an R&D lab that is working on other problematics such as object detection, advanced geophysical tools. And this might also, in the future, some of these functionality could be implemented in the platform. For this release, the two main strategical themes were, we were focused on these themes, and I'm going to present the main highlight of this release. So first, we have integrated the FAST technology from Bluware. So Emmanuel, can you maybe move on the slide? Perfect. So we have integrated that technology to allow you to stream seismic volume stored as a VDS format in the OSDU data platform directly from PaleoScan. That functionality will be provided as a beta functionality for free in the core application until January 2023, in order to foster the collaboration and the exchange with our key customers and build with you the next step of our VDS OSU journey. We have also done some work on boosting the performance of the 2D workflow and enhance user experience globally. Finally, in the coming weeks, a new byproduct will be released, the PS Data Loader, and this is mainly addressing data management team, and this will allow you to import, preview, quality check input data, and also export all the objects of PaleoScan and generated outcomes. So that should be released in a few days, weeks. Okay, so I think it's time to start. I will give the floor to Aurélien and Jean-Philippe. Thank you for joining and enjoy this technical forum.
Thanks, Marion. Yeah, thank you. Good morning, good afternoon, and good evening for everybody. I'm Jean-Philippe Adam. I'm sales manager for Europe and Africa for Eliis, and I'm glad to have Aurélien Van Lennep with myself to present one of the new features of PaleoScan 2022 and our journey to OSU. I will let Aurélien introduce himself and then share my screen.
Hi, everyone. So I'm Aurélien Welden from Bluware. I'm a geoscientist by background, and I'm leading the business development effort for Bluware in the EME region. Really happy to be here today with you.
Okay, I will share my screen. Yeah. Okay, let's start with this first presentation. And this first presentation, it's about our PaleoScan journey on OSDU and how we embedded the fast adaptive streaming technology into PaleoScan. First, before to start, as Marion explained, but short review of OSDU data platform. On OSDU, Eliis is member of the OSDU Forum since 2020. And the main objective of the OSDU data platform is to disconnect the data from the application and to be data-centric and not application-centric. And like this to speed up and unlock the workflow between different software and allow more collaboration. In the spirit of OSU and the openness, OpenVDS is now a default OSDU format for action for the seismic. And of course, Segway is still using as input for OSDU seismic domain, but the VDS and OpenVDS, it's now used as default format for the exchange. And to accelerate the interpretation cycle, we are a strong relationship and strategic collaboration between Eliis and Bluware. Before to start the part of PaleoScan and how we embedded the FAST technology, I will let Aurélien introduce the VDS format to you.
Thank you, Jean-Philippe. So, our industry is using a lot of different formats for seismic. We know that SegWy or SegDs are the main standards, and then every application has its own format. So for PaleoScan is the PS file. For us at Bluware, we've been working for the last 15 years on building a new format that enables very rapid access to any part of the data, and that's called VDS and stands for Volume Data Store. So that's a bricked format that enables extremely rapid access to data, metadata, inline, cross-line, time slice, sub-volumes, or random 2D tiles in any part of dataset. It's also supporting wavelet compression and adaptive streaming, which is the topic of the talk today. And also VDS is very, very flexible and supports multiple level of details, which is what you need to accelerate visualization workflows. It's also a multi-dimensional object, so you could store 2D lines, 3D volumes, but also gathers and even higher dimension data. And in 2019, we gave an open source API to the OSDU forum to enable clients and software vendors alike to be more familiar with the format and also adopt this new technology in the frame of their digitalization initiatives. So a quick word on adaptive compression, what we mean by that. And you can see on this slide, it's a journey through SegWy to VDS and looking at different ways to write and access a VDS file or object. So if we start in the left, so you see the legacy format, which in our case would be SegWy. That's not a compressed format. And let's say its size is, because it's not compressed, is let's say 100% of the size is this data set. So once you go to VDS, there's several options. One is called true lossless. And by true lossless, we mean really true lossless. So you can always go back from VDS to SegWy, and you get exactly the same file. And the idea here was that you shouldn't be afraid of losing any information when going to a new format. So we created this true lossless. And even without signal loss, you can see that the size of the file is already reduced by 20 to 25%. So that's already a good step. And our recommendation when you go to fully lossless VDS is really to preserve the data on, let's say, cold storage, for example, or Glacier in the cloud. Now, for most workflows, you can actually compress the data a little bit, and that's what we call virtually lossless. And then you can reduce the size by almost 80% without losing any critical information. It means that we lose less than 0.5% of the data. So this is very, very stable numerically. You can use this level of compression for any type of amplitude, AVO, or seismic processing process. So there's really virtually no loss in the signal. But for data managers, it's a massive change because your file is reduced by a fraction. And then you can decide to either write with even more compression for specific workflows, or what is more interesting is to stream with a specific resolution or tolerance towards workflow. So you can still have virtually lossless in your storage, but stream only what you need to the application. So let's say you stream 2% of the data for a visualization workflow, which is transforming the performances. And this is what FAST, our transcoder, is all about. Next slide, please. Yes, thank you. So with FAST, it's what we like to say that FAST is like Netflix for seismic. It's really about streaming data from one source and sending it on demand as requested by the end user application. And that's what we do with Netflix, right? If you look at on a movie on your phone, you don't need the 8K resolution. But if you work on your nice home cinema system, then you want best resolution. And the key is really to start from one file and then stream what you need. So, and in our industry, we like duplicates, and that's an issue now because everybody shoots larger surveys. We shoot OBN data sets, so the size is just going up. And here I want to show you what's actually happening when you buy a survey from any vendor, and its size is 200 gig. So that's a segue. Then you need to load it in your application, which can be application X, PaleoScan, or you want to keep segways or raw data, and then you add another 800 gigabytes on top of your 200. And then, PaleoScan, as you know, needs extra volume to accelerate its performance, to have better access to inline, crossline, or time slice. So you need to generate those files and write them down before you can accelerate your workflow. So that's another 400 gig. And then when you work on really large data set, then usually it's common practice to cut in subvolumes or decimated volumes and then accelerate the workflow. So if we start with 200 gig, then with all this, let's say preparation of the data, you can end up at 2.4 terabyte. And that's before you actually start your workflow. So the idea with VDS is to solve some of these issues by having, feeding the end user application with the data through adaptive streaming. So here, we start with a single source of data in VDS in OSDU, and then we deliver this data as needed by the application. So we keep, the performance from internal applications format or optimized volumes or sub-volumes. So we keep or increase the performance, but we basically stream through creating a virtual folder on the end user platform, and then your PaleoScan will access this data as it's accessing a PS file. So this is really transforming, I think, data access, and that's what OSDU is all about: is enabling data liberation through standards. So here VDS for seismic. So I think that's it for me. Jean-Philippe, the floor is yours.
Thanks, Aurélien. And thanks for the presentation of the FAST technology and VDS. Now, more about the PaleoScan journey on OSDU. As Aurélien explained, now PaleoScan is connected to OSDU data platform thanks to the FAST technology. Okay, you have your cloud with your OSDU data platform, and we can connect directly with FAST, and like this we can stream directly volume directly into PaleoScan. This is for the input of PaleoScan, and then all on the current application of PaleoScan, on the current release, we still have the local data store. After the streaming, if you compute a new volume, if you compute a model read, it's stored locally on the local data store on premise. Okay, this is the current status of our OSView journey. It's working with, I will show you during the live demo, on AWS and Azure directly. And then, just before to start the live demo, just a short comparison between the two workflow, the import base, the traditional workflow of PaleoScan, and exactly the same workflow with the adaptive streaming workflow with thanks to FAST. Okay, we have a segue of 52 gigs, and first we start to import this volume into PaleoScan. And due to the size of the survey or the geometry of the survey, you have some area without data, and the size of the inline volume is 81 gigs. And then, as Aurélien explained, we have some optimized volume to display the volume in inline and crossline. Due to this, we double the size of the volume to have the inline, to have the crossline and the time slice. And then, of course, we start the normal workflow of PaleoScan. We create a model grid. To create this model grid, we need to smooth a little bit the volume to help PaleoScan to propagate the automatic propagation through the volume to have a better automatic propagation. And to be able to use this volume to interpret, we duplicate with the crossline volume. That means we have 81 gigs more just for the volume. And then we create the model grid, just the skeleton and all the node with the connection. It's 10 gigs more. And then we compute the relative geological time volume with the inline and crossline. At the end, we have a total amount for the size of the project of around 550 gigs, sorry. And it's you just start the basic workflow of PaleoScan. After, you have to compute your horizon stack if you want to do some sequence stratigraphy, etc., etc. Now, okay, thanks to fast technology and VDS format, we can directly stream from OSView this volume. That means, okay, we stream, and for our PaleoScan format, no need to have the inline, also the crossline and the time slice, because thanks to the brick format, we have the same performance as optimized volume directly with the streaming option. And we can, and this volume will stream into PaleoScan and will be recognized as a normal volume of PaleoScan. That means I can use this volume for a model grid or to compute an attribute, etc., etc. And just thanks to the streaming, we just save all the import and the visualization stage of the workflow. And then, of course, as I explained, we will store all the output of the workflow, the conditioning volume, the model grid skeleton, and the RGT on the local store, exactly as before. But just with this workflow, we save more than 200 gigs of the project, okay? Without compression, with the true lossless option, we arrive to 380 gigs, and with the compression, we arrive to 290 gigs, okay? With a virtual lossless, the compression used for the application. As you can see, it's more than 50% of the size of the project reduced just thanks to the import. As you can see, it's very useful, especially if you have huge volume in terms of if you're working in exploration, for example, like this, you can win a lot of space just by streaming the VDS from OSView directly, thanks to the embedded fast option into PaleoScan. Just quick summary, and then I will switch to a live demo. As you can see, the fast option and the streaming option allow two things. We skip the import step. That means you will win a lot of time. No need to import, duplicate your inline, crossline, time slice directly, and you have a centralized data access. Also, if other application X using also VDS, you increase the interoperability between different applications, and like this you have more flexibility for the workflow. And the most important point, you reduce your storage space and your cost, especially with the cloud. We know that the space on cloud, it can be very expensive, and due to this, you will drastically reduce the size of your storage, especially thanks to the streaming, because you can stream into PaleoScan, and you can, as you can see, reduce the size of your project by more than 50%. But this workflow can be done with other applications. I will just switch to a small live demo. Just give me 1 second. Yeah. Okay. This is my PaleoScan environment. I already import a PaleoScan format. Okay, I will just open just to show you. We have, okay, we can open, we can navigate through this volume. Okay, I will just navigate through the volume, and I have the same kind of navigation as before. This dataset, it's Australian dataset, it's XMOOS Basin. But now we have a new option. It's our OSDU connector. I just have to click on it. And then I can choose Amazon or Azure as web services for OSDU. I just have to click on connect, and then I can search my volume. I can type, or I can just click on search to find all the volume available on my OSDU data storage. Then I can, I have all the information. We have two different volumes for XMOOS. This one, it's a true lossless option. I just have to put a name, okay. No compression. I can choose the inline crossline, and PaleoScan will mount this volume into my project browser into PaleoScan. As you can see, I have a small Bluware icon just to know it's a stream volume. I will import also a second volume. It's the virtual lossless. It's the one we can use for application and just to compare the navigation and for the workflow. I will just close, and then I just have to double click exactly as a normal volume to navigate. This volume, it's the true lossless. Okay. As you can see, I can navigate into the inline exactly as my PaleoScan format. Exactly the same with the virtual lossless. Of course, we apply a small resolution. We will compare a little bit after the two volume. I can navigate through the volume directly. And then, we'll just reorganize a little bit. I will just compare my different volume. Okay, I will open my PaleoScan format. The one, the true lossless and the virtual lossless. I organize my windows. Okay, exactly as a normal volume of PaleoScan, I can just change the color bar. Okay, I can change the color distribution, etc. as a limit. I can then drag and drop to the VDS volume. Okay, I just have to click, and then I can drag and drop directly my volume. And then, okay, I will just compare the amplitude. I will just zoom on one area. This is my PaleoScan format. I will just zoom on the true lossless. And the most important, I will zoom also on the virtual lossless volume, okay, just to compare between virtual and true lossless. As Aurélien explained, we have a very small loss between the two volumes. And as you can see, you can use the virtual lossless to do your interpretation and your workflow into PaleoScan. Okay, I will just continue to show you it's exactly a normal volume as a PaleoScan format volume with different options. If I click on the volume, I have access to the property of the volume, just reorganized to have more space. With the PaleoScan format, I can compute a real-time attribute, for example, as RMS amplitude. Okay, I can zoom in, I can navigate exactly as before. This is a PaleoScan format with the normal way of navigation. I can do exactly the same with VDS format stream, thanks to FAST application. Okay, with the true lossless, as you can see, I have the same navigation. I can still change, of course, the parameter for the RMS amplitude application, and exactly the same for the virtual lossless. Okay, I will just also compute my RMS amplitude. I can, of course, change my attribute as sweetness, as seismic release, for example. And then, okay, one of the main problem of PaleoScan format is I need to compute the crossline and the tab slash values. I don't have this problem with VDS format because thanks to the VDS format, crossline, for example, it's already compute. Okay, no need to spend time to compute the VDS. I just have to click on the volume manager and I can switch to crossline. Exactly the same with time slice. I will just switch off the real-time attribute because the real-time attribute it's only compute on the frame. I will just switch off and I just have to click and then I can display my time slice. Okay, and it's displayed on the fly. No need to compute to store the optimized volume orientation. It's already compute and I can still display very quickly. As you can see, it's a really important step in terms of exploration. If you have big volume and you need to import them to compute the crossline, the time slice, it can be time consuming. It's a lot of space. Here, I just have to click on the OS view and PaleoScan will stream the 3 direction directly into my PaleoScan project. I will just finish this presentation just to show you it's a normal workflow. I can compute my model grid. And as you can see, the 2 Bluware volume with VDS format are stored with the icon, and I can use for the model grid. I just have to choose, and then I have to choose my parameter, the polarity, the patch size for the horizontal distribution. I can, of course, use all the advanced options, the horizon, for example, restriction between 2 horizons, etc. And then I will compute directly. Okay, I already compute my model grid, and I will use this model grid, okay, to start my interpretation and start my workflow to create my relative geological time model and then my horizon stack, etc. I will just come back to my presentation just for short conclusion. Okay. Just a short conclusion. If you remember the phase 1 of our OSU journey, we don't have this link to OSU. Currently, okay, if you want to store the output of PaleoScan, for example, the relative geological time model as VDS format, it's not possible. We work on it maybe to implement export, for example, and then push back and ingest output from PaleoScan into OSU. And like this, you will be able to connect and then push back all the results to OSU to share with other applications. Thank you for your attention. Sorry, I don't check if we have some question during my presentation. Maybe Manuel.
Thank you very much, Jean-Philippe and Aurélien, for this very instructive presentation. Yeah, we do have some questions for you. We have one question here saying, I missed the introduction. Is this new feature or are you just patching this streaming feature? Can you elaborate a bit on any potential legal confidentiality issue with the data stream? I don't know if that's for you or for Aurélien. Maybe you can have it both.
Yeah, I will start and then maybe let Aurélien. Yeah, concerning PaleoScan, yes, it's a new feature of PaleoScan 2022. The fact we embedded the FAST solution and the button we have into PaleoScan to allow you to directly stream all the and check all the volume available on OSU. Concerning the other part, I will let Aurélien on the VDS part.
Yeah, sure. I mean, the idea here is not to change where the data is located from a legal point of view. The idea is really to accelerate the workflows. So if you're on-prem and you want to use, an OSDU platform on-prem, then the data stays on-prem with all the, the regional regulations you might encounter. The data is not gonna necessarily move to the cloud if you don't want it to be in the cloud. Maybe you want a private cloud or a closed region on AWS. So, I mean, down the line, the idea is to not touch anything linked to confidentiality or legal framework. It's really OSU compliancy and performance related. innovation.
And for the presentation, we show you the connection on OSView. Of course, it's possible, as Aurélien explained, to stream from other cloud. It's not available yet into PaleoScan, but we will see in the future. And
thank you, Jean-Philippe and Aurélien. I think we have time for one more question before we move on. Of course, we can see all the questions here, and we will answer to all questions afterwards. So this question is, does the VDS format allow for random lines to be visualized on the fly?
Okay. With the format of VDS, now, yes, it's possible, but not on the current, because it's a brick format and we can access just to the part of the volume. It's not available yet into PaleoScan. Currently, you still have to create your line and then display your line. But yeah, thanks for the suggestion, and Marion is on the presentation. We will write on the request suggestion.
Okay, thank you very much, Jean-Philippe and Aurélien. I know it's we didn't have a lot of time for the Q&A, but we will answer you all of your questions. So now I think it's time to call for Benjamin and Matthew for their presentation on this integrated seismic interpretation to structural framework workflow. Benjamin, can you please? Yeah, here you go.
Hi, good morning, everyone. So my name is Benjamin Jaros. I'm a geologist working at Eliis, and actually with Matthew and Schlumberger, so we have developed an integrated seismic workflow between Schlumberger and Eliis. So I will just leave the floor to Matthew to introduce himself and start talking about the workflow.
Yeah, perfect. Thanks, Ben. So during this presentation, we're going to show you the connection between Petrel and PaleoScan that we've developed together. This was through a collaboration with one of our major customers that really inspired us to bring together some core technology aspects in the two different platforms. So we're going to take you through an explanation of the workflow that helps you to achieve and walk you through a demonstration of how we might apply that to a specific data set. But first, before we go into that, I want to talk about why we embarked on this journey together. Really, it was because we face a number of challenges when trying to characterize the subsurface. Really, and those challenges that we face as geoscientists really impede our efficiency to characterize the subsurface and produce model outcomes that we can use to drive decisions. So when you're operating multiple software platforms, it can be very difficult to transfer data and maintain its fidelity. It's also the case that when we bring together and collate subsurface data to build a reservoir model, we can have quite significant disconnections between the various interpretation stages, and that can result in inconsistencies in data and obviously produce poor results when we create a subsurface model. And that requires then painstaking reconciliation in the reservoir modeling platform to produce a final result that is consistent and is ready to move forward into the various stages of reservoir characterization. So ultimately, this means that the timeline to produce all of the required inputs and the final model is lengthy, and this delays business decisions, but also impacts the quality of those decisions. So what we've implemented together is an integrated workflow that has the potential to change the way that you work to build subsurface models when working between the two applications, Petrel and PaleoScan. And to achieve this, there are a couple of specific developments that we embarked on. So the first is enhancements that Eliis made to their connector to support the transfer of triangle meshes from Petrel to PaleoScan. And the Schlumberger team added a new process inside Petrel to automate the extraction of data from a relative geologic time model and then incorporate it to update a subsurface framework model, a structural framework model in Petrel. And through having this workflow, then you have the capacity to easily add structural constraints from the faults and horizons in Petrel into the PaleoScan software and use them to constrain your relative geologic time model, which really starts to bring together this consistency of interpretation between the two packages. So essentially, with these additional tools, it's now possible to have a more integrated workflow for subsurface characterization across the two platforms, and that starts with Petrel, where we generate the structural constraints. So in this case, we generate the structural constraints in the form of a fault framework, and that fault framework can then be coupled with bounding horizons if you generate those, and then passed over to PaleoScan in order to produce a structurally constrained relative geologic time volume. And once that relative geologic time volume is generated, we can then take that, use a reference stratigraphy through a reference well to extract new horizons from that volume that we've generated and incorporate them directly in our subsurface framework model to update that model. And really, this is an iterative workflow where we may produce a number of different relative geologic time models, as you'll see today, as we start to converge on the appropriate solution for our interpretation. So let's have a look first at where this modeling journey begins. It really starts with, of course, generating interpretations. So this could mean machine learning interpretation or various interpretation techniques to generate fault interpretation. And we take those directly into a process in Petrel called fault framework, and we use that to build a fault model with the fault relationships embedded inside that model. We then can optionally interpret horizon constraints within Petrel or within other software to then constrain better the model grid interpretation when we start to move and generate our model grid and ultimately our relative geologic time model. So let's take a look at this workflow in action. So here we're starting in Petrel. From Petrel, we have our interpretations. Here you can see those interpretations being restricted to the data set. This is the XMETH data set, and I've inserted those in the fault framework process. And running that process, I'm then able to generate a fault framework and QC that fault framework. I can also interpret horizons, as I said, interpret those consistent with my structure. And then ultimately I can take those horizons and use those with a defined volume of interest to generate an initial structural framework model. Of course, I can edit the fault relationships in Petrel so I can control how the different faults are connecting and produce a representative interpretation of the subsurface structure. And in doing that, when I then produce my structural framework model, I can then have a well-defined interpretation and ultimately model of the subsurface stratigraphy. And in this case, you can see that I've got a major unconformity, and then I've got a relatively conformable sequence in blue. And it's this sequence that we're actually going to then take into PaleoScan and refine using the RGT methodology to update and then really add additional resolution to that structural model in Petrel. So in order to do this, we need to transfer the data to PaleoScan. Here. So the first process that I need to run in order to do that is I need to convert my fault framework model to triangle surfaces. So you see I right click on that and I convert to surfaces, triangle surfaces, and then I perform the same for my model horizons. In this case, I run a simple workflow just to generate surfaces and ultimately interpretation that exists everywhere in the model. So those object types can then be easily added to the PaleoScan connector, where I can drop in a folder of surfaces, various interpretation objects, and you can see here I'm selecting all of the triangle meshes that are represented by my fault framework, and I can send those directly to a PaleoScan project. And those will then be the foundation for constraining my relative geologic time model in PaleoScan. And so Ben's going to take over and continue the workflow on the PaleoScan side. Ben, over to you.
Yeah, thank you, Matthew. So I think, Matthew, you need to go on the next slide. Yeah, perfect. Thank you. So So now actually the data have been successfully transferred from Petrel to PaleoScan. Because it is 3D data, the next step is to create the grid. So I'm going to click on the first icon to create the model grid. I will enlarge the window, and the idea is to select the seismic that we want to use as an input. Because we don't want to create the grid on the entire data, the idea is first to bound it between two surfaces that we have previously interpreted in Petrel and imported within PaleoScan. So the horizon one, I'm going to use the top model horizon coming from Petrel. I will drop in it, and I will just repeat the operation for the horizon 2, but this I'm using the base model horizon. To better constrain and consider the seismic event we're going to use to bound the grid, the idea will be to shift up and down these two surfaces. So this is a new feature that we can now do straight in the grid. So for the upper horizon, I will just type -100 meter to shift the upper horizon upward. And I will just repeat the operation by typing +100 meters to shift the lower horizon downwards. Then once it is done, I will go back into the model grid parameter. I will just put the seeds somewhere in the data. And in here, because the data is fairly chaotic with a quite discontinuous signal, I will just reduce the patch size down to 3. I will just keep the polarity as it is, peak and trough, and I will, of course, use the faults as an input. So I'm going to drop in the faults in here and the fault in the seismic viewer, so we can just take a look at them. Then I will just click on test parameters. So PaleoScan is going to create a small grid around my seeds with the parameters I have set, and this will allow me to test the parameters. So of course, PaleoScan will consider the fault I have used. So PaleoScan will stop the propagation against the fault to avoid having wrong connections. So we can see that we have a nice geomodel. So now let's just display the model grid. We can see the nodes are bounded between the two surfaces I have used as an input. So it seems quite okay. And so now it is done. We can click on save. PaleoScan is summarizing the parameters I have set, sorry. And now I can give a name, click on save, and PaleoScan is going to run the grid, the model grid. So now we're gonna move on to the next slide, Matthew, please. And actually, so now PaleoScan has generated 2 files. Okay, so we're gonna have access. So it's the next one, Matthew. Sorry. Okay, so now perfect. So now PaleoScan has generated two files. So we're gonna have access to the initial grid and also the automatic interpretation. So we have to start from the automatic interpretation. This is where PaleoScan has created the entire set of horizons. So PaleoScan will open 2 files. So we're gonna have 2 windows, sorry. So I will just tie them horizontally. In the upper window, we're gonna have access to the to a cross section, an inline, and in the lower window, we're gonna have access to the time map. So now our job is just to see what PaleoScan. We have to QC what PaleoScan did. So we're going to digitize the horizons. And now the idea is just to connect all the patches together. So you can set the horizons are well constrained by the faults. Okay, so this will prevent PaleoScan from making any wrong connections. And so to connect the pieces, I just have to click once, and PaleoScan will link all the patches to create the horizons. Once the horizons are complete from wall to wall, then the idea is to validate it. So we can click on the M icon, we will mark it, and PaleoScan will assign a specific color to this surface. And of course, the idea will be to repeat the operation all over again for the other surfaces. So I will just display another seismic event. I will just click to connect all the pieces. So now I am on the edge of the survey. So I'm just gonna move the other way around. And PaleoScan will just keep connecting all the pieces this way when I just click on a seismic event. Again, I will just validate this horizon here by hitting the M icon. And of course, the idea will be to repeat this over and over until we are running out of time. So I'm just gonna show you what I did. So I have QC'd this horizons in a couple of days, so in just 4 days. Okay, so far everything looks quite okay. So now the next step is to create the geomodel. So because I didn't spend too much time QSing the horizons, I will just increase the interpretation size to a maximum, okay, to avoid having some gaps. For the same reason, I will decrease the link probability to 1, and I will also drop the faults, so PaleoScan will consider them for the generation of the relative time domain. Then I will click on save. I can change the name if I want, but I will leave it as it is. I can click on OK, and so now PaleoScan is about to run the geomodel. So we're going to have a new file stored in the application that I will then send over into Petrel, and so now I will just leave the floor to Matthew.
Perfect, thanks, Ben. So now we have this additional interpretation data that Ben has generated, and the really important fact about that is that it's consistent with the structural interpretation in Petrel, the fault framework. And so then I want to use that new and updated interpretation to incorporate that information to update my structural model and refine the zones. So as I mentioned earlier, to do that, I'm going to take a reference well with its stratigraphic interpretations, in this case, a set of well tops, and then use that to then generate additional inputs to my model and update that structural framework. So you can see here what I'm aiming to produce. So I'm going to walk you through that process. So to start with, of course, I need to first actually import that data into Petrel. And so again, one second, let's try that. Okay, nice. So in order to do that, I can use the connector to select the volume that I'm interested in, and I can import that directly into my Petrel tree. So once I've done that, I have a geomodel. I can play with its display settings and visualize that in my 3D window. So you can see here now I've got a relative geologic time volume in my 3D window. You can see my reference well located there in the center of the 3D window. And now you can also see a process here, which is activated by right-clicking on the structural model. And by opening that process, I can then select the existing horizons in the model. I can correlate them to events in my well-top stratigraphy interpretation. And where I have additional well-tops that don't currently have corresponding horizons, I can then select to extract new interpretations from that volume based on the intersection of the well tops with the RGT volume to generate new interpretations that are constrained by the fault interpretation due to the consumption of that in the RGT creation. And then I can also automatically update the model. So when those are extracted, I have an option to decide if I want to automatically include them in the model. And if I do so, then I produce horizons like you see here. So you can see I've refined that structural model. And then, of course, I perform regular QC. So in this case, I can see a particular area of the model where I actually have some inconsistencies in the throw at the contact between the horizons and the fault. And I can highlight that even more obviously using an attribute called fault throw consistency, which I can compute on the fault surface. So here you can see in the areas where the fault surface is red, I have inconsistencies between the throw and my model. So really this is suggesting to me I need to go back and improve the way that I produce this model. And looking at the data, I can actually compare the RGT volume and see that there are some inconsistencies here locally. So I'm going to feed that information back to Ben, and Ben is then going to go into PaleoScan and then update that location. So I mentioned to Ben the location of the area, and he's going to take a look. So Ben, over to you.
Yeah, thank you, Matthew. So now I have this feedback from Matthew. So the idea is to go back into PaleoScan. I will just take a look at the geomodel. So I'm going to open it up. I enlarge the window. I will synchronize both windows, so the seismic and the geomodel. Okay, then I will zoom in. And actually, Matthew told me that the discrepancy was in the cross line, in the crossing direction. So I will just flip the seismic into a cross-line direction. I will just type 12,701, which is the location of the discrepancy. Then I will do the same for the geomodel. And actually, when I zoom in, then we can just clearly see the discrepancy here in the geomodel. So the idea will be to go back within the grid, the model grid, okay? And I will just keep refining the patches. So I will just keep connecting the patches. So you can see that now I'm just enabling the patches. So we can see the yellow patches. If I just take a look in the geomodel, we can also see the yellow patches in here. So it gives me a feedback, okay, on what will be the next geomodel, actually. And I will just keep refining the grid this way. So of course, the model grids or the geomodel won't be updated on the fly. Okay, so I have to recompute a new one. So that is why I will click again on compute geomodel. I will use the same parameters to be able to really compare both geomodels. I will just then click on save. I will just name it V2. I will click on OK, and PaleoScan is going to create a second version for the geomodel. So now I will just move on to the next slide, and actually I will just be able to compare both versions of the geomodel. So I'm just gonna open the V2. Sorry, Matthew, I think it is the next one again. Yeah, perfect. So now I will just open the V2, okay, which is the second geomodel I have created. So then I will just enlarge the window. I will just flip it into a cross line. So I will type 12701. Then I will synchronize the two windows to apply the same zoom factor. I can cross navigate and zoom in. And actually, we can see that in the upper window, which is the second version, the geomodel looks much better. So I have I have enhanced this version for the geomodel. So now this geomodel looks much better. So I can just send it back to Matthew, and he can consume it in P12.
Great. So you can see that in PaleoScan, Ben has now updated the volume of stratigraphy, and I'm going to consume that in my structural model. So I simply repeat the steps that you saw previously. I find the volume that I need in Petrel. I import that into my Petrel project. Once I have that volume in my Petrel project, I'm then able to consume it to update the model. So you can see here that IGT is more consistent in this area. So I use an option to replicate the structural model just to copy its parameters to create another version of that. I drop, in this case, the new volume into the model, and I just rerun it. And straight away, that's going to run through the process to extract those horizon inputs and update my structural model. And then I can compare side by side those two models. So you can see here the throw consistency attribute is now telling me that I have a consistent throw sense. And as you can see, because we've updated the entire sequence of interpretation in PaleoScan through the IGT, I now have very consistent horizon fault intersections in the sequence. So it's quite a nice iterative workflow between the two applications where I can consume updates as they're produced by Ben in PaleoScan to update my structural model. So really you've seen that end-to-end workflow now where we've gone through the generation of the constraints in Petrel using the fault framework and additional interpretation and horizons. We've passed those over to PaleoScan using the data connector to facilitate the transfer of data. We've then constrained the volume in PaleoScan using the IGT process and taking the inputs from Petrel. And then we can take those iterations that we produce in terms of the IGT volume out of PaleoScan, consume them in Petrel and update our structural model. And of course, it's not enough just to consume those on the first iteration. We need to QC the model rather with the various iterations as we produce the the outputs and see the areas where there's improvement, and then we can have that feedback loop with the PaleoScan technology. And of course, once you're in Petrel, the advantage is you can continue the workflow. In this case, you can take the full resolution of that framework that you produce to produce an unstructured grid or a stair-step grid, and then run that through the full reservoir property modeling to simulation workflow. So the transition from that structural framework that's consistent with the interpretations in PaleoScan is simple to then transfer to a structural model, a grid that we can then use in property modeling and reservoir simulation. So really what we showed you were the changes in PaleoScan in terms of updating the connector to support triangle meshes to really facilitate this workflow, a new process in Petrel to make it much more efficient to consume the outputs of RGT, and then really how we can connect that together in an integrated workflow. And the aim, as we said at the start, is really to make sure we have much better integration between the software platforms, have that consistency in terms of the interpretation and ultimately the structural model, and reduce the cycle time required to produce interpretations and a model of the subsurface. So with that, I think there might be a few questions in the chat, so let's take some time now to answer questions, and I think Emmanuel is going to pass those out to Ben and myself.
Thank you very much, Matt and Ben. It was a very great presentations. It's very interesting to see how this workflow can speed up the whole structural modeling process. So thank you for sharing. Yeah, we got some questions in the chat, so I apologize for the questions tab, as it seems that it doesn't work properly and people cannot see each other questions. So it's a good idea to use the chat going forward. So we've got a question here. Hi, Benjamin. Can we create a horizon stack from the model grid in which horizons will follow the specific polarity?
Yeah, hi, Dovana. Thanks for the question. Actually, it's a good question, and it is now possible to do so. So we have different ways to create the horizon stack. So usually we go through the geomodel, okay, because it is complete throughout the entire survey. But actually, we now have an option where we don't need to create the geomodel to create the horizon stack. So straight from the seismic, we can create a horizon stack using all the marked horizons. So we first need to mark all the horizons. We need to QC them to validate them. And once they are marked, then we can create a horizon stack with these marked horizons. So that's something doable.
Thank you, Ben. There is another question here. Is the geomodel import into Petrel already available? If so, which versions of PaleoScan connector and Petrel, and how will these become available? Through core or specific module?
Well, actually, this so the geomodel import was available since the beginning, because for PaleoScan and even for Petrel, the geomodel is a volume. So it is a classical Segway format. So since the version 1 of the Petrel connector, actually we can import the geomodel from PaleoScan to Petrel, and you can even import it back from Petrel to PaleoScan. So that's something that is doable since the beginning, actually, of the connector.
Okay, good. Thank you, Ben. I've got a question to Matt. Does this work with all types of structural framework, or only depot grid, or also pillar gridding or staircase gridding?
Yeah, this is a good question. So the structural framework process in Petrel, as we highlighted, is a way to produce a representation of the subsurface structures. Underlying that is a tetrahedral mesh representation, and we use that in gridding workflows. So there's three options in Petrel. The first is to create a depot grid. That's a simple process where you can define the gridding resolution and produce a model that represents the full subsurface framework because it's a cut cell grid. But optionally, you can also generate a stair-step grid using the same similar UI. If you want to produce a pillar grid, it's a little bit more involved. You have to convert out the resulting model to the pillar fault model and then regenerate the horizon model. But it is possible to do so.
Good. Thank you, Matt. I've got another question for Ben. How do I know the model grid is refined enough?
Yeah, so that's a good one as well, and actually we have so I didn't show you during this demo, but actually we do have access to a preview. So because of course, when PaleoScan does an interpretation, it is hard to see what PaleoScan thinks and what PaleoScan will do. So actually we have an option in the MoneyGrid viewer, which is called a preview. So the idea will be to display the preview. So this way we know what PaleoScan is doing. We know where PaleoScan is struggling with the interpretation. So this way we know where we have to put our hands on, and we know where we need to help PaleoScan out. So the idea will be just to take a look in the properties of the MoneyGrids. You have to activate the preview, and if the preview looks good enough, then you can just move on with the generation of the RGT.
Very good. Thank you, Ben. I've got another question for Matt. How can I get access to the seismic stratigraphy process in Petrel, and with which version was it released?
Yeah, this is a good question as well. So this comes as part of the core licenses in Petrel. So if you have access to structural framework, you'll have access to the process, and you can select that by right-clicking on a subsurface framework. And we made this available in our 2021.1 Petrel release. So anyone using 2021 with a core license has access to this functionality. Of course, they need the connector and PaleoScan in order to complete the workflow.
Great, thank you. Thank you, Matt. Another question for you. Are there options in the seismic stratigraphy process to extract horizons and review them separately before running a model update?
Yeah, I think this is an important one because sometimes we know with complex models, the runtime and complexity in generating them can mean that it's very useful to QC the inputs before starting the process. So we did add an option to that utility to extract horizons and generate horizon interpretations in the input tree without updating the model. And you can first then review those, understand areas where maybe you have inconsistencies before updating the model. But it is nice to generate the model because, as you saw in the demo, we can run QC on the model with things like looking at the offset on the horizons at the faults and things to then really understand how consistent the structural interpretation is and ultimately the structural model is.
Thank you, Matt. I've got another question for Ben. Can I bring horizons from Petrel as constraint in the model grid of PaleoScan?
Yeah, exactly. That's something doable. So here, actually, the horizons we have imported from Petrel have been used as bounding surfaces to limit the grid. But actually, we can also use horizons as a constraint. Okay. So the idea is, I don't know if you remember, but in the presentation here, we saw two files, the initial grid and the automatic interpretation. So if we want to import horizons and use them as a constraint, we have to start from the initial grid. Okay, so we open the initial grid. So this is the grid with all the links, but with all the nodes, but without any links between all the nodes. So we open the initial grid. We load the horizons in. So PaleoScan will just we'll try to snap the horizons to the closest patches. And once it is done, we can run a second automatic process. And from there, we can keep moving forward with the workflow. So that's, again, something doable.
Good, thank you, Ben. I think we have time for one last question. It will take more time to create horizon stack, and many horizons which we mark are not consistent at all. That's why we don't have a good view of horizons at all. Is there a simple way? I think that's for you, Ben.
Oh, sorry, actually, I was reading as a question. Can you repeat the question? I'm sorry.
I think it's the same that we're reading. It will take more time to create horizon stack, and many horizons which we mark are not consistent at all. That's why we don't have a good view on horizons at all. Is there a simple way?
Oh, well, actually, it won't take more time to create the horizon stack from the micro horizons, because the horizons are already marked. So PaleoScan will just combine all of them in one single volume. So it will go even faster because we don't have to go through the creation of the geomodel and then the horizon stack. So it won't go, it will actually go faster. So that's, I guess actually that's the easiest way to create the horizon stacks from the model grid. Yeah.
Just Ben, may I just add a comment? We are planning to add in the short term, I don't know if it's going to be in January or next June, but an option to directly create an horizon stack from a selection of horizon in the horizon list directly. So that would allow you to pick the horizon you want, either marked or not marked, and directly from that selection create an horizon stack. So that would allow you to save quite a lot of time. And actually, it's already in a beta version, but we will release it in one of the coming versions.
Thank you very much, Marion, Benjamin, and Matthew for these presentations and answering those questions. So with that, I think I can wish you a very good day or a very good evening, and I hope to see you soon. Goodbye, everyone. Thanks for the thumbs up. See you soon.